I work as stream-based, early-stage startup, working on unlocking access to Kafka through different means, also kind of we'll cover in the talk. I'm Roman. I joined a wee while ago. I'm principal engineer there and mainly working on the Iceberg projections over Kafka. And that's going to be the focus of our talk. So we're going to go over a few sections of the talk. What's the problem? Why we're doing it? What is Apache Iceberg? How we can do it on Kafka, how it maps to Kafka concepts. A little demo. And then after we saw the demo and how it's done, why we are doing it and what it unlocks. So in modern world, all the kind of data processing is moving more and more towards real time, especially for operational workloads, transactional workloads. Things need to be processed right now. Bank transfer going through. It's not a person somewhere in the bank that received a letter with an order to do a transfer that processes it, and a few days later things happen. It's right now. You click the button, you scan something, money is through. Maybe there is a fraud detection. Again, you want to discover it and act on it, on something suspicious, straight away, not sometime later, when the money are gone already. Maybe you're monitoring IoT sensors and some parameters are out of whack. Again, you want to shut down the machinery or investigate immediately. But for real-time processing, there are caveats. Experimentation is difficult because the pipelines are quite rigid. Things have to be predefined ahead of time what you're doing with them, because it's not point in time. You're not writing a query where you're saying, give me something over the last months with those parameters. You're setting when the message arrives, I want to apply certain rules and do certain actions. But all those rules have to be predefined ahead of time. Therefore, discoverability is quite low. You can just poke into the real-time system, into the stream of events to see what's the shape of the data that I have, what all the different bits of data I have at hand, how can I join them, what can I do with them. And as well, window sizes are small, because you're reacting in real time. Your data arriving and you're doing some decision. You're not doing a scan over historical data that's long in the system. Now, on the other hand, the batch processing allows to do all that analysis, all the different shapes of data, all the different joins, all the different correlations over months of events, what the trends are, how the seasonality affects, for example, product selection from users, and things like that. But setup time is quite high for them, because they're complex jobs with lots of joins, a lot of correlations, a lot of rules again, and they're quite rigid. If you're doing batch processing and you're pre-computing some dimensions, if you don't have the raw data that you use to pre-compute them, you can't really go back and recalculate how changing some parameters would look like. If you're, for example, storing hourly aggregates of purchases of people, you can go back and look how mid-hour data looks like at 5-minute intervals or whatever, because you already discarded that. You only have your hourly aggregates at that point. At the same time, partitioning and things like that, how do you lay out your data affects it a lot. For example, with the same Iceberg, when you go to it, you can prune data based on partitions, but you define partitions when you store the data, so changing that layout is quite expensive because you need to go and rewrite everything again in a different shape. Excuse me. Now, to deal with real-time demands while keeping batch level of processing, there are different architectures that emerged, as you can see, quite a while ago. Probably most of you heard of them, Lambda architecture and Kappa architecture. So in Lambda architecture, we have two processing streams, or two parallel processing engines. One that deals with batch processing, and one that deals with real-time processing. Usually they utilized in a sense that the batch processing gives you kind of cutoff points of processed data, and then speed layer can fill the bit that you haven't processed yet, to give you the more real-time kind of complete view of it. For that, you would utilize the mixed query here, but then the mixed queries becomes quite complex because you need to do the union between the batch system and real-time view system. And at the same time, your rules need to be written both for real-time system and for the batch system in two different languages, in two different paradigms. So you have two different code bases and frameworks that need to calculate the same kind of results. And then any changes in one of them need to be reflected in the other, kept in sync, lots of problems. And of course, like operational burden, you have two completely separate systems that need to be maintained and operated on. Now the Kappa architecture proposes a different approach. You process everything as a stream. It doesn't matter if you're doing historic data reprocessing or the real-time processing. You load everything and you process it as a stream. Because you can read the historic data as a stream of events as well. It doesn't need to run SQL over scan. It can read the same old data and just push it one by one as a hose, and you apply your stream processing on it. So any changes in processing require, of course, replaying of the whole stream. So you need to have long data retention on the source data. Plus, you need to be sure that you can replay and reprocess that historic data in sufficiently reasonable time to be usable. So if you have 20 years worth of data, that is petabytes maybe, and you need to change small calculational bit in your processing function, you need to reload the whole petabytes of data through the stream processor to recalculate all the outputs, which can be really resource intensive, of course. And I guess one of the bits that is even more restrictive in that paradigm is expertise. There are a lot of people that know how to work with SQL. They know how to work with big MapReduce, Hadoop-based kind of jobs, but reasonably not as many people know how to use stream processing well, because it requires a mind shift. The processing on stream processing is different. You can just take the SQL and throw in and say, oh yeah, just process it one by one. You need to think about it really differently. You need to know about windowing, how different windowing affects things, how to use local state stores, how to work with that processing paradigm. So neither of those architectures really hit all the marks. Like, it would be nice to have something that can be more amendable to both approaches. Because, again, different workloads require different processing system, or would work better with different processing system, and would be more kind of hybrid. And combining both stream and batch processing is still really hard. More in reality, you'd have operational side that does some stream processing, and then it's a connector, it's a sink, it's all loaded into the data lake, data warehouse, and then batch processing applied on it somewhere there. But then you have, again, the same kind of problem. You have operational side with people that know what's in the operational state. You have analytical side with people that know what's in analytical state, but they don't necessarily know what's in the operational state, what data is actually available to them. They only see what is being sent to them, not what they could get from the operational system that's not being sent to them. Now, I'm going to talk a little bit about what Apache Iceberg actually is. There is a lot of hype recently about Iceberg. Iceberg is a new hot, one of the new hot kind of paradigms, and rightly so. It's an interesting idea and it's an interesting concept. But some people sometimes don't really know what it is. So Apache Iceberg is an open table format, mainly for huge or big analytics data sets. It came from the same backgrounds as Hive and MapReduce and Hadoop systems, big data processing, when we have a lot of data that's being sunk, and we want to be able to process it reasonably efficiently. It doesn't try to compete with Oracle Exadata or even Postgres on the data sets where Postgres or Exadata and so on are good at. It's more for the big data processing when you're not really in super rush to process it. You just want to be able to churn through lots of data in reasonably well. Now, Hive was quite good at it as well, but because it emerged from HDFS and folder-based structures, it had limitations that Iceberg set to overcome. But actually, like under the hood and conceptually, they're not that different. Now, it's not a storage engine, it's not execution engine. Iceberg doesn't run your queries, like at all. It doesn't care. You're running your queries in Spark, in Presto, in Trino, in BigQuery on Google or whatever. Iceberg just says how the data has to be written, so that all those query engines can read that metadata and read the data and understand and know what to look for. So they can be coded to expect certain metadata so that they can understand where the data is and how it's shaped and run compute on it. Now, there are multiple layers to Iceberg, typically represented like this. That's from the official Iceberg documentations. So at the very top we have Iceberg catalog, and its only real job is to implement the asset transactions. It holds the table information, what all the tables that are available, and what is the current metadata file. So whenever the write happens, let's say Spark or whatever reads the data, and it reads the current version of it. So let's say it read metadata file as 0, that's current right now. Then whenever it commits, it goes and checks through the catalog. Is the current metadata file still as 0? If it is, commit is accepted, and it does atomic swap, and points now that current metadata file has snapshots as 0 and as 1, and it's all fine. But if something else wrote that second metadata file by then the commit is rejected, and it needs to rerun the whole operation and do the write again. So it's optimistic locking through that single point of Iceberg catalog to implement the atomic swaps. But it's just holding really metadata pointer, and does that kind of commit processing. Not even processing, just the check. Now we have metadata files. They show what the current snapshots are, what the current snapshot pointer at the moment is, what partition and schema informations are for the table. And then down it goes in layers. We have manifest lists that group the manifest files, which group the data files. Again, it's mostly for efficient pruning and limiting amount of metadata the compute needs to read during query planning. So again, when we are doing, let's say, select everything from our table where we are looking for data just for the March of 2025, and our partitioning is based on hours, days, months, something like that. It can read just down to the manifest lists or manifest files, depending on the structure, and then not scan all the files that don't fall into that bucket of March 2025 for the partition. In addition, there are lower and upper bounds on the columns to enable the pruning, but that's kind of it. Now, differently from the databases, in Iceberg we have no indexes. There is no reverse lookup index, there is no way to look up exactly the row or entry in the Iceberg file. It's just pruning based on those partitions, eliminating the files themselves from the scan. And as I said, what it enables is that we can have all the different clients, as long as they talk Iceberg, let's say protocol, like understand Iceberg table format, they can all work independently with our stored files, but be different implementations. It's not a single point, like everything has to go through Snowflake engine, or everything has to go through BigQuery engine, or some other engine. As long as they use writes through Iceberg catalog. For reads, they actually don't even need to use the Iceberg catalog, as long as they can find the latest metadata pointer in some other way. For example, BigQuery external Iceberg tables allows you to just drop in the JSON file with the latest metadata into the location and point BigQuery to that location alongside with your Parquet and so on files and metadata files, and update it by some trigger by yourself. But it's your then job to update it to be most recent when some writes occur. Now, how can we do the Iceberg on Kafka? In general, like Kafka does streaming messages, it's events on the topic. Iceberg works with Avro, Parquet, files in a bucket, with some metadata on it and catalog pointing what the latest snapshot of it is. Like two completely different systems. Can we bridge them, and how? Let's talk about JBob. Not this JBob, a different JBob. Let's think as just a bunch of bytes. So we used to think about events on Kafka as events. They represent something, there are some messages. But really they are just bytes. Let's say your topic has 1 million Avro events, Avro encoded events. If you would take that 1 million events and put them on the file system as files, maybe group them so they're not one file per event, would it actually semantically change a lot of things? So Kafka characteristics, Kafka has efficient sequential reads, like it's good when you're reading through the topic from start to end. It has some data organization. We have our events grouped into topics, and minimalistic indexing. We have timestamps and offsets for events, and a bit of sharding based on partitions in Kafka. Yeah? Now, for the projection of Iceberg over Kafka, what we really need? We need to represent tables. We need to present schemas for the data that we have. It would be nice to have some partitioning there so that we can do a bit of pruning and not just scooping everything all the time. And then we need data in compatible format. Now, Iceberg supports Avro, Parquet, and ORC out of the box. So if we look at the topic as a table, we could represent Kafka clusters as namespaces within Iceberg ecosystem, topics as a tables, messages as a row in our table, and then field within a message as a column in the table. It's not really far-fetched. It's quite close in there. Now, if you take the building blocks, where we have Kafka that produces metadata layer for us, which has topic metadata with topics, offsets, and their partitions. We have schema registry, which gives our schemas, and the actual data layer where our data topics are, our bytes sitting on the topics. Now, we built two other services to enable the Iceberg projection. So first of all, we built the storage gateway, which does aggregation of events on Kafka into the chunks represented as files in S3-compatible file system. So if you imagine have S3 bucket, which is Kafka topic, so whenever you do ls or list buckets, we can just go and query what topics are available on Kafka during execution of it. Then if you're doing a fetch of a block of offsets, so if you're going my topic slash partition 0 dash offset 1000 dash offset 5000, we can go and fetch offsets from 1000 to 5000, get those bytes, stitch them together into a single file using Avro container file encoding rather than per message encoding, which encapsulates the schema at the top and then writes Avro rows basically into that file and send it off. And it comes over S3 protocol as a file that we can now present as a base data layer in the Iceberg projection. Now, on top of it, we need metadata so that we can generate all of the Kafka metadata layer. So basically our layers of Iceberg become, we have a custom REST Iceberg catalog, which instead of just saying here are the tables that are on the file system created somewhere on S3, can query Kafka to say what topics do I have. Those topics are your tables. And then whenever we load the table, it can generate the needed metadata bits to say, okay, this table has 50,000 rows, because it knows that it can query Kafka at that point to say that the topic has 50,000 offsets on it from earliest to latest. The schema is such and such, again, fetch from schema registry, here's the schema for those messages, and so on. And then manifest files can chunk that range of 50,000 offsets into pre-configured chunks to serve them as, for example, 5 files of 10,000 offsets each over that ephemeral S3 layer. So our Spark SQL, for example, analytical application can query the Iceberg catalog, which then can query the Kafka for all the data, and return it as a Iceberg table metadata back to it. Now, the way Iceberg clients work, they just query the catalog for the metadata bit, the JSON bit. And the JSON bit would have the location like S3, warehouse, something, something, manifest.avro, manifest list.avro, snapshot data.avro. So all those files are actually then loaded through the I/O layer of the Iceberg client. So it would go to the object store, to the S3 or Google or whatever, and load them from there. So all of them have to be served through our ephemeral S3-compatible layer as well, in which we can proxy them back to the ISK, which knows what they should contain and build them again on the fly to send it off backwards. Now, that is quite nice, because that allows us to load the data at query time. So there is no delay, there is no stream processor or something, some preparation step basically, that says, okay, I'm preparing the data and it's ready now, and then sometime later I prepare the next chunk of data, and sometime later I prepare the next chunk of later. Whenever you're querying it at that exact moment, we query the Kafka and we can say, that's the latest possible point in time right now what's on Kafka. There is nothing missed from that. It still enables us to do some pruning. We can do partition-based pruning, Iceberg partition-based pruning, based on Kafka message timestamps. So all the messages have both offsets and timestamps are contiguous because they are based on wall clock basically, or depending how you configure it, but generally based on either log append or the produce timestamp. They're all growing and they're sequential in general. So you can still do the per hour, per day, per month, and so on, splits of data and prune out if your query contains the parameters only looking at this slice of time, not to read anything outside of it. And at the same time, Kafka has partitions, which are usually based on message key and hash-based bucketing of them. So again, that translates to Icebergs bucketing partitioning as well. So if your query is only querying for something like transaction ID 1234, it can eliminate a lot of the stuff that's in the partitions that it doesn't fall into. It still needs to scan a lot, it still needs to scan the whole partition. It's not an index, it cannot go directly and just say, yes, transaction 1234 is offset 500, just fetch that one offset. But it still does some pruning. And there is basically no overhead when it's not in use, because all processing happens at query time. There is nothing that needs to be prepared behind the scenes all the time, maintained, and so on. So if you have, let's say, 200 topics, but you're only querying one of it, it's fine. Like, there is no overhead to cover all the 200 topics. You added another 10 topics. They can be available on the Iceberg projection straight away. You don't need to pre-process them or look at them, do something with them to make them available. They're there. Now, if you add indexer to that, which does require scanning of data as it comes into topics, or rescanning it at some point, we can do a bit more interesting stuff. Adding an indexer enables more flexible partitioning, because then we know what data is actually on topics. So if there are topics that contain data that have something in payloads, that again is either written in chunks or in some contiguous ranges. For example, even the timestamp, that's not really Kafka timestamp, but actual transaction timestamp. That may be close enough to it, it's kind of going increasing over time, but you might have like late arriving messages that have a timestamp that doesn't really match your Kafka timestamp exactly. You can still base your Iceberg partitionings and based on them, and whenever you run your query, grab them precisely, even if it would overshoot the Kafka's timestamp a bit. and then pre-calculate column statistics for data pruning, because Iceberg allows minimum and maximum values within data file in the metadata, so you can eliminate those that don't have it. So again, let's say we have transaction IDs, and they span there from, I don't know, A to Z, and then some blocks only contain D to O or whatever, and you're looking for a transaction ID that starts with B. You straight away know that those blocks that have minimum value above B can be discarded. You don't need to consider them. So all those, they don't have it. So it's like negative pruning. Now let's do a little demo. Now it's all on my local, just because I usually prepare it to run just from my laptop. Sorry. So I'm not depending on the Wi-Fi connection and internet gods and things like that.
100% betting on Wi-Fi connection to my demo. When you're betting on Wi-Fi connection, you say that, oh yeah, that's work because of Wi-Fi.
Yeah, but you know. So, demo. Let me go to my trusty terminal. So let's say we have a topic that has some data on it. Transactions. Yeah, it's on terminal, so it should be. I can make it even bigger if. Yep. So let's say we have some topics that has some transactions, and we want to find all the transactions that belong to single branch. Let's say bank branch or whatever, branch 120. We can do it with Kafka tooling. We can use Kafka Cat, for example. Why do we need anything else? Oh, wrong folder, of course. Kcat. There we go. So we can go to our Kafka and say, give us everything, and then grep on the branch ID that equals our value. OK, that's not great. It didn't find anything for me now. But you know what I mean. Like the tooling for querying Kafka is, give me everything. You can specify an offset and a timestamp, because there are parameters you can specify to look up your stuff. But that's it. Then you need to build something, some inclusion, exclusion, some processing. I'm not going to say all the tooling, most of the tooling that you see in the wild work like that have the search boxes, like lenses, different UIs for Kafka. They all work like that. You specify some predicate or some criteria, and you just do the search and scope the topic and applies it and excludes everything that doesn't match it. Now, if you go to do the same thing, but with the power of Iceberg, we can spin up our Spark. I hope it's going to work, because now it's scaring me. Maybe I should have relied on Wi-Fi instead. Now again, granted it all runs on my laptop, it's a little bit sluggish. It's both Spark and Kafka and whatnot. Yay, we have Spark SQL. So we can use our ISK namespace and catalog, and do show tables. And we have our topics as tables. Here we go. Great. And now we can do the nice select again in normal SQL. It will take a bit, because again, it runs on my local laptop, and it's a bit, but it's reasonable. So it took about 5 seconds to fetch 33,000 rows out of about a million row topic, or million events topic. Now to make it a bit nicer actually looking, I have a different little setup that I spied with my little eye from a person standing there, doesn't pay attention.
I'm trying to make it look better on the camera, so nothing very much.
So I've noticed there is a tool called PopSQL that knows how to talk Trino, and it looks quite nice. And then Trino can talk Iceberg. So in PopSQL, we can go and write our nice and slightly more complex queries than we can do with Kafka Cat. For example, like select rounded sum of transactions when the transaction type is withdrawable, do it as a minus, otherwise keep it as a plus from our topic, and group it by branch, join on branches to get the branch name rather than just the ID, and group it by branch, and so on. And I'm not sure what it's doing here. I think it's already not connected yet. And then it allows to map the same thing onto different graphs and have nice looking widgets with stuff, if it works again. Pum 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 pum. It doesn't like me today. It really doesn't like me today. What is with my Trino? Trino is working, all there. Let me check. Sorry, technical troubles. Where's my Trino configuration? There. Yeah, so just to highlight it, again, I'm using the REST catalog, probably not very easy to see, but I'm using REST catalog on my local host and the same S3 with a overridden endpoint pointing to localhost where my server is running right now in my IntelliJ. But it's not liking it in Trino for some reason. Liked it in Spark enough. But the point is, you have your normal SQL to run over the queries, run over Kafka data as it is a database or as an Iceberg. Yeah. And without writing stream processor just for that end of month calculation, 360 view, or investigation, maybe something spiked on the risk analysis and you want to go and dig into your transactions. Don't need to go and unload all the data from Kafka to somewhere to be able to slice and dice it. You can just do it straight away with your normal SQL and your normal kind of analytical tools on whatever the latest there is right now. Let's move on to it. So why we are looking at it is exactly this, to have a single platform for batch and real time, to be able to access the same data that you have, and primarily we are thinking that the data is still primarily in operational systems, in real-time systems, not in S3 sitting somewhere. Your freshest data is there in your streaming layer, because that's where you're processing it in real time. You can't make batch faster. Like, you need to process stuff in real time, so the data is going to be in the real-time layer. Anyway, again, as little as possible per topic setup and overhead, so that you're not in that world that we are now in, when you need to set up connector per source topic or per set of data. And then when someone asks, what do I have there? Oh, we don't have a connector. I can't look at it. I need to ask some team to go and set it up so that it can be loaded into my analytical things where I can poke at it and query it again. Simplifies the discovery and experimentation. Sometimes it's enough to just put an hour brackets, so you're not scooping whole topics there, but you just want to poke at it and see what it looks like, what data I actually have. What if I join this with this and that? What can I see? And reasonably consistent non-functional requirements. So again, the access is based on Kafka layer access. If you can access it on Kafka, you can access it through this projection as well. You still use the same Kafka, like username, API keys, and so on. They restrict, so you have your Kafka's RBAC, ACLs and everything controlling the access to it. And we have that kind of unified Lambda Kappa or just streaming batch processing architecture where, depending on the type of query, so mostly real-time queries, that I'm at least interested, but depending on the type of it, if it's a push query, when you have something that's waiting for events and reacts to them as they come, application to application, generally, stream processors, and so on. Goes directly to Kafka, streaming layer, works fine. When you have pull query, when you have AI agent, not just necessarily a person, maybe a person asking a question. Is there a delay with flight 1, 2, 3, 4? Is there fraud risk, or are transactions with withdrawals greatly above transactions with deposits for this day, for this branch? Is it running out of cash in the vault in the branch? You can run it through the projection on the same set of data at the time when you need it. Maybe you only need it once in a blue moon. You don't want to build a stream processor that tracks it all the time for all the branches if you're only going to use it once a month on 3 branches out of the whole set. And then the mixed query becomes an interesting one as well. Now, instead of having a connector or some job that lends the data from Kafka or streaming system into the lakehouse or analytical system, you can have an incremental batch job that you run once an hour, once a day, that just does, insert, which one is it? Select into or insert as select, basically, because on both sides you have your same SQL. You can just write the SQL job that loads that slice of data from Kafka, lands it in the lakehouse, and then when you're querying it, you can do a union, and you have your mixed query all written in SQL, loading the historic part from the lakehouse, union with the latest stuff that's still on Kafka, the last hour of it since the upload was run, and you have the real-time results with the latest data, but fetched from 2 separate systems at the same time, but now using the same SQL, the same language, the same protocol, and the same architecture rather than mixing the 2. And of course, batch queries become much easier. We're kind of moving master data from the Lambda architecture that was just in the batch layer back to the streaming system, Kafka or whatever, if it suits. If you have infinite retention, tier storage, things like that, it actually can work quite well. Now you can do your, I would say, your cleaning probably always going to be on your stream processing. So you want to make sure that the data that you're querying at this point is already validated and actually shaped correctly. You're not going to be doing query directly on the raw data that is not even checked for conformity to schemas that might be bad. So you have your kind of bronze to silver thing on the stream processing layer, but then the silver thing, once you've done your operational stuff on it and so on, you can analyze it and query it straight away from the analytical systems. Oh, I actually had a separate slide for that, but I just talked about it. So all that. And thank you.